Hello and welcome to Physical Sciences. My name is Themba Ncube. Today we are looking at electric fields, one of the sections that have to do with electrostatics. And, mentioning electrostatics, we can immediately recall that we've managed to look at, some of the aspects that are built up to electric fields in terms of how point charges interact with each other, in terms of the forces, be it attractive forces between opposite charges, or it could be, repulsive forces between like or similar charges. These are some of the little details that we already know by now. Now let's quickly look at, the outline in terms of the concept map of the sections that we've managed to cover leading to electric fields. Okay, right. Now we have managed to look at conductors and insulators in terms of materials that carry charge or exclude charge, right? We also know something about the fact that the quantity of charge remains constant in a closed system, which is the net charge. That has a lot to do with the principle of conservation of charge. Now, in terms of origin of charge, we can immediately recall that we are saying that, for a material to be positively charged, it needs to, lose electrons. For a material to be negatively charged, electrons must be transferred to it. And we also dealt with a very, very important concept of quantization of charge. Exactly what do we mean when we talk about the fact that, just to remind ourselves that what exactly do we mean when we say charge is quantized? Remember, every charge that exists in the universe is actually a scalar multiple of the number of electrons either removed so that we get a positive charge, or number of electrons added so that we get a negative charge. So that's exactly what we mean when we say charge is quantized. Hence, it gives us the formula, Q is equals to NE. So the Q is equals to NE is actually the principle of quantization of charge. We shall talk a lot about vectors today in terms of, the forces that other charged particles experience in an electric field. And the concept of electric field is not exactly far removed from the Coulomb's law, because the Coulomb's law says to us the electrostatic force of attraction between any 2 point charges is actually directly proportional to the product of the charges and inversely proportional to the square of the distance. So the Coulomb's law has to do with the electric fields as 2 point charges interact in space, and the electrostatic force is precisely a non-contact or a field force. So the type of force can either be attraction, which is opposite charges, or repulsion, which actually has to do with like charges. Right. Let's look into the thinking exercise part of our session today. This is the thought that maybe should drive our session today, so that we are able to discover some of the very exciting scientific facts as far as electric fields are concerned. So the main idea is centered around how can we determine the direction of an electric field. Now, the moment we say direction, we are immediately thinking about vectors, okay? Hence, I indicated earlier that we shall talk a lot about vectors as quantities that have got both magnitude as well as direction. So how can we determine the direction of an electric field around a positive or a negative point charge? That's the main thing that we want to, at the end of this session, that we must be able to demonstrate, okay? And then secondly, what causes the magnitude and direction of an electric field at any point to vary? To vary, it means it keeps changing. Now, this drives us to the point that, say, we shall be talking about what is called a non-uniform field. Remember, an electrostatic force is actually a field force because it's a non-contact force. Now, why does the magnitude of that force change as we vary the points within an electric field due to a point charge? Right. Okay. And then the keywords. Now, when it comes to the language or the terminology, these are the basics that by all means we need to get right, because the terminology has to do with the concept, and the understanding is based also on the language. So we shall try and break it down, into smaller bits so that we try and manage and navigate our way through it, right? So the first term is an electric field. We have already managed to look in the previous sessions leading to electric fields. When we looked at Coulomb's law, we spoke about what an electric field is. So this is a region in space, okay? So this is a region in space wherein an electric charge, okay, what happens to this electric charge? Where it will experience an electrostatic force, okay? So this force is an electrostatic, which is non-contact force, right? So if we subject a charged particle to an electric field, it experiences an electrostatic force. An electrostatic force in its own right is it's a vector quantity, right? So electric field is just a region in space. So you must be able to distinguish between electric field and electric field at a point. Electric field at a point, symbol E, right? This one is a vector quantity, right? Why are we saying it's a vector? Because an electric field at a point is actually the force experienced per unit positive charge, right? The force experienced per unit positive charge. Now, we'll try and break down what we mean exactly by unit positive charge, right? So this is the force experienced per unit positive charge. Now, the term unit suggests that there is one, okay? One of whatever. We talk of a unit. So the SI unit of charge is actually the Coulomb, right? So if we're saying that it's the force that is experienced by a unit of charge, it means it's the magnitude of force that's experienced by 1 Coulomb of charge. And that 1 Coulomb of charge is always taken to be as a positive charge. Sometimes we refer to it as a test charge. So the word test charge will be used interchangeably with unit charge to refer to one and the same thing, right? So the unit charge is the SI unit of charge, which is plus 1 Coulomb. Hopefully we're fine with that. Right, we've managed to look at vectors in terms of quantities that have got both magnitude and direction. So the emphasis on vector quantities is magnitude, right, and direction, right? So the direction part is the most interesting one, as you'll discover as we move along, you know. Then we've spoken about the unit charge, which is the plus 1 Coulomb. Okay, and this is, hence we're saying it's positive unit charge, all right? And then non-uniform. If a field is non-uniform, it certainly means that within that field, if you randomly pick a point in the field that is caused by a particular point charge, the magnitude of the force that the test charge will experience at that point will vary, depending on a number of factors as per the thinking that we started with. At the end of the session, we want to discover as to what exactly affects the magnitude of electric field at a point at the end of the day. That's what we want to drive it. So remember, when we talk about the non-uniform field, we are saying electric field at any point will vary from the next, right? Okay, and then part of the understanding is that if you have, for argument's sake, a point charge, we can immediately know that, okay, as long as it's a charged particle, around it, there's this region wherein another charge will experience an electrostatic force. But by merely looking at the charge, we do not see the electric field, but we can only observe the effect of the electric field on other point charges. Hence, we want to look at what we refer to as the properties of the electric field lines. So to represent these electric fields in theory, we would use what we call the electric field lines. Now, we want to look at the properties, a brief discussion on the properties of electric field lines. So these electric field lines are imaginary. The term imaginary explains itself. It says it means these lines don't actually exist in real life. What that simply means is we use these field lines to represent the field, but these lines are not there in reality, right? Now, secondly, they are three-dimensional. Okay, let's break this down. We live in a three-dimensional space, you know. We're saying that if this is a charge, now the electric field is not only confined to this plane, it is in all the planes you can think of. Hence, we say the electric field around a point charge is actually three-dimensional, right? And then, thirdly, the direction of the field lines at a point is the same as the direction of the force on a positive point charge at that point. So this is basically what we talk about when we say, how do we determine the direction of the field around a point charge? So the direction of the field is actually determined by using the unit positive charge, which is what we're going to discuss shortly, right? Furthermore, it says here, the field lines do not cross. So when you draw the field lines, make sure that these lines, never mind they're imaginary, one of the properties is that in their representation, they should not overlap each other. Hence, we're saying the field lines do not cross, right? And then field lines are perpendicular to the surface, right? Now, if they're perpendicular, it means then if we have got a charge, particularly, be it a positive or negative, they need to touch the surface, whatever the direction could be. This is one example. It means it has to touch the surface of the point charge in our representation, right? Then we talk about density of field lines, right? Just to break it down a little bit. When we talk about density, we're talking about, you know, it could be the ratio of, you know, mass per unit volume as we know it, but how close these lines are, it suggests something about the density of the electric field lines in their representation. So the closer the lines are, the stronger the field at that point. So that's a very, very important, you know, explanation to say, why does the field vary, and why do we essentially say the field is actually non-uniform, right? So we shall talk a little bit more about that. Now, here's a scenario where we want to use a simulation, because some of these concepts, you know, they're a bit abstract, and, you know, just to create those mental pictures, it becomes difficult. But we have a tool, a resource here, as a simulation in the form of a simulation that I would like us to use, right? Say, for argument's sake, we take a positive point charge, right, and put it there, okay? So there is a point charge. Even if I move the point charge, the field still exists. So, but you'd realize that the field lines are pointing away from the positive charge. We'll explain that, because if we take, say, for argument's sake, a test charge and subject it to this electric field. So when we say the field is a region in space where another charge will experience a non-contact electrostatic force, this is exactly what we mean. So if we take a point charge and put it there, you know, a unit charge, can you see that the unit charge is experiencing a force away from the charge that created the field initially? So this is actually the force that is experienced by the test charge. So the sensor actually, in this case, it represents the unit charge. So we can either move the unit charge closer. As you can see, as we move it closer, the force gets bigger. But as we move it away, further away, the field becomes weaker. Why? You can check, guys, the density of the field lines is actually greater, closer to the charge than as you move further away. Hence, the force experienced by that test charge will also change. That's the idea, right? Okay. And then moving along, so if we were to represent the electric field around a positive point charge, as we have seen in the simulation, we are saying that around this, the lines must be perpendicular, right? And they must move actually away from the positive point charge. Why? Because that's the direction of the force that the test charge experiences, right? So this is the electric field around a positive point charge in space, right? And then similarly, we would also have the same demonstration to represent. Oh, actually, this one needs to be towards. Why? Because it's negative. We'll try and show that very quickly, right? So if we talk of a negative point charge, it means then the force must actually be towards the negative charge, because the test charge is positive, or the unit positive charge is positive, meaning that it will experience an attractive force towards the charge that creates the field, right? So this is basically what we're talking about, right? So that's a representation of the electric field. But the properties are also consistent in terms of that these field lines must be perpendicular, they must not cross, you know. The closer you get to the charge that creates the field, the stronger the field due to the density of the electric field lines, right? Now, if we can quickly go back to our demonstration, we would have a situation whereby let's use a negative point charge for argument's sake. You know, it also shows that, okay, the direction of the field is towards the negative charge. Now we can use our unit positive charge, place it in the field anyway. It could be anyway. You can see the force that acts on it is actually towards the charge that creates the field. And again, the closer we get to it, the greater the force. The further away we move away from the charge that creates the field, the greater the distance, the lesser the force experienced by that unit positive charge, right? Okay. Having said that, I think it also makes quite a lot of sense for us to say this is the representation of the electric field around a negative point charge. So that's as far as we can go for the first segment. In the second segment, we shall look at the electric field patterns or lines between interacting point charges. Let's take a short breather for now. Welcome back to our second segment. We want to look at more, concepts around electric fields. We've managed to look in the previous segment into the field as a result of a point charge in space. Now we want to look at a scenario where we've got 2 point charges interacting in space and want to discuss, the understanding around the electric fields due to those 2 point charges. Let's take, for argument's sake, 2 like charges which are actually positive, right? So these are like in the sense that they are both positive. Electrons have been removed from each one of them. Whether they carry the same magnitude of charge or not, it's something else. But the fact remains, these 2 point charges are actually like, right? Okay? So if we were to, say for argument's sake, use 2 point charges, we've got 1 point charge, there's an electric field around that point charge, which is a region in space in which an electrostatic force will act on another charge. Now, there's just 1 charge. What if we place another positive charge at some distance, okay? Now, you see there is a pattern there that we can immediately pick up. In both cases, these are actually pushing away from each other. So in our representation, based on the properties of electric field lines, would know that these 2 are actually repelling each other. So the force experience is repulsion, right? Now, you can think of repulsion in terms of pushing away, because, at a very basic elementary level, we would understand that a force essentially is a push or a pull, right? So the force that exists between these 2 is actually a force of repulsion, okay? So these are the field lines as a result of that, okay? Now the direction, very, very important, it's away from the positive. That won't change, that fact still remain. So we are saying the direction of the field is actually from positive to negative. So if we've got a scenario like this, it means these are actually pushing away from each other, okay? Right? So that's the force, is from the positive away. So that's the direction of the field pattern. So that's how we represent the repulsive forces that exist between 2 positive point charges, right? And also the force that exerted, if this, let's say for argument's sake, was Q1 this side, and then this was Q2, okay, this charge Q2, we can immediately tell that the force with which Q2 pushes away Q1 if I were to draw a vector diagram, would have, that's our Q1. So this is the force of Q1 by Q2, and then equally so, this is the force by Q1 on Q2. This is by Q2 on Q1. So this is force by Q2 on Q1, right? And then this is the force by Q1, okay, on Q2, right? Now, if these vectors, we were to take them into account, we would understand that as per the Newton's third law, because these are object A and object B, so you'd understand that F Q2 on Q1, okay, is actually negative F Q1 on Q2, right? What does that mean? The direction is opposite, yet the magnitude of the forces are equal, okay? Same magnitude, but opposite direction. Are these two vectors equal? Not exactly. Two vectors are only equal if they've got same magnitude and same direction, right? So just to bring enough, some concepts that are related to this that we need to also remember, right? Then what if it was two negative point charges? Still, these are like charges. The variation in this case, or the difference, is that these ones are actually negative, right? Having said that, let's go back to our simulation and see the pattern that exists around negative point charges if there are two of them in space interacting with each other. Okay, that's the direction of the field. It's towards the negative, but in both cases, they're actually pushing away from each other. So this is the field which in real life we do not see, because we said that these field lines that we use to represent the electric fields are actually imaginary. So we're still pretty much talking a lot about the properties of these electric field lines, right? So still it's repulsive, but pay careful attention to the direction, right? Pay careful attention to the direction, right? Pushing away, again this side, pushing away, okay? Remember, they need to be perpendicular. It means they need to make contact with the charge. Now the direction is towards the negative, however, they are still pushing away from each other. Why is the field towards the negative? Because in that electric field, we shall go back very quickly and demonstrate something very critical in terms of the direction of the field. So if we go back to that, you'd realize that if we take a sensor or our unit charge, place it there, it would show that it's actually towards the negative, okay? Even here, it's towards the negative. Wherever you put it, it's towards the negative. That's the direction, okay? But the closer you move, the greater the force in that field. But the further away, we shall talk to that again in our next segment, right? So this is basically the properties of the electric field lines as we have demonstrated in as far as like charges. Now let's look at a case where they are opposite or unlike, right? If, say, we've got a positive and a negative, whether which one is the first, it doesn't matter. The fact remains that these are what we call opposite or unlike. So the term unlike can be substituted with what? Opposite. It's appropriate in this case. Okay, in terms of charge, that one is positive and the other one is negative, right? Now, if we first of all look at the demonstration on the simulation, just to show the interaction of those 2 point charges that are opposite, this is what happens, right? Okay, let us put it there. Okay, you can see that the direction is still actually away from the positive, but towards the negative. Even if we take our sensor or our unit charge, you see it experiences a force towards the negative, but always away from the positive. As we draw closer to the positive, you can see the force experienced by that unit charge is actually away from the positive towards the negative. Towards the negative, we are consistent with that, right? So this is just a demonstration of the interaction of 2 opposite or unlike charges. So now, if we were to use the electric field lines once more, there is a force of attraction between them, okay? The direction is from positive to negative, right? Remember the properties, the lines must not cross, and the direction is from positive to negative, right? Away from the positive, we're still maintaining that, right? And it's actually towards the negative, as we have demonstrated in the simulation. So usually if you were asked to actually represent, if electric field pattern, you could get easily 3 marks. These lines must not cross each other. The shape of the pattern should be, correct, as well as the direction. So those are 3 very essential components of electric field lines in terms of point charges, right? Okay. Now let's look at a case where we want to determine the magnitude and direction of electric field at a point. Now, we talk of electric field strength at a point, but we actually refer this to as electric field at a point, right? Let's break it down now, okay? So it's electric field at a point. Now, when we talk about electric field at a point, that's the quantity E, which is a vector quantity. So the emphasis on direction cannot be overemphasized. And then when we talk about strength, would alternatively be referring to the intensity. Okay, we're still talking the same language. We're still talking about the intensity of the field. How strong the field is an indication of the force experienced by a unit positive charge at that point, right? So from the definition, we know that electric field at a point is actually force experienced per unit positive charge. So the force is in newtons, right? So the force is in newtons, okay? And then the unit positive charge, okay? That's the unit positive charge. The unit positive charge has a unit of a coulomb, right? So in other words, the unit of electric field at a point is actually it's a newton per coulomb, right? So it's a newton per coulomb. This is the SI unit of electric field at a point. It means the force, how much force will be experienced when we subject a unit positive charge to that field. So in other words, say for argument's sake, we have got, let's say we've got, for argument's sake, 15 newton per coulomb in whatever direction. What does that mean? It means the unit positive charge experiences a force of 15 newtons. That's how strong the field is at that point. Now, let's understand that, say for argument's sake, we've got a positive point charge in space. Around that positive charge, point charge, what exists is an electric field, right? As we have established in earlier demonstrations, okay, that's an electric field. Now, that electric field in this case is in that direction, okay, because the force is a vector, and so is the electric field at a point in that field. Now, if we say, for argument's sake, we've got point X there, right, and point X is at some distance, say distance R from the surface of the charge. Now, and then at point X, we place a unit positive charge, okay, Q plus, right? Now, there is a force that exists between the charge that creates the field and the unit positive charge. And what that force is actually, we can determine it using the Coulomb's law. So we know that from the definition of electric field at a point is force per unit per coulomb, which is the force. In other words, we can immediately say, if we make the force the subject, we get F is equals to E or multiplied by Q, right? So we just rearrange this to that, okay? And then again, we appreciate the fact that according to Coulomb's law, we know that the force is equals to K, the charge that created the field, the positive charge that was placed in the field, which is this one, right? divided by the square of the distance between them. So that's another F. So if we equate these two, in other words, we get EQ, which is the F, this F, right? And then this is equals to K, Q multiplied by unit charge over R squared. Now, you'd realize that the test charge, the unit charge, is the same in both sides of the equation. Then we get electric field at a point due to the charge that creates the field is equals to K, which is the Coulomb's constant, multiplied by the big Q, which creates the field, over R squared, which exactly is this formula, right? So the question is, when do we use this formula? When we have got the magnitude of the charge that creates the field. Whereas this one is merely a definition of what electric field at a point is all about. Now, in the coming segment, we would want to use this to actually determine the magnitude of electric field at a point, given some examples, so that you get a sense of what exactly we're talking about. Let's take a short break for now. Welcome to our third and final segment of our session. We're still talking electric fields. We've managed to look at the concept around how to determine electric field at a point due to a charge that creates the field. Now, we want to look at a typical example as to how do we do the calculations around electric field at a point in terms of magnitude and direction. Why magnitude and direction? Because we've emphasized the fact that electric field at a point is essentially, a vector quantity. So hence, we need to emphasize on the importance of direction. And once again, how does direction come in as far as electric field at a point? We know that in an electric field, as a region in space, if you subject a unit positive charge to that field, it will actually experience an electrostatic force. Now, in terms of direction, it's actually the direction of the force that is experienced by that unit positive charge. So I will try and look at a typical example. There are a lot of mathematical skills that come in. You may not always be required to calculate the electric field at a point. Sometimes you may be given the electric field at a point. You may need to determine the distance of the point from the surface of the charge that creates the field, or sometimes you may not know the magnitude of the charge. So it could work either way. We need to be flexible around. Hence, the understanding behind that becomes very, very critical. Right, let's look at a typical example in this case. It says, calculate the electric field at a point. Okay, so this is what we're looking for, right? So if we were to collect the data, we'll say E is equals to a question mark. This is what we want at the end of the day. Now, it's at a point that is 6 millimeters, okay? What is that 6 millimeters? R is equals to 6 times 10 exponent negative 3 meters, right? We'll talk about that briefly in terms of conversions and SI units, right? And then we also told that the charge Q1 has a magnitude of negative 15 nanocoulombs. So what is this exactly? This negative 15 nanocoulombs. So this is actually the magnitude of charge Q1, which is minus 15 times 10 exponent negative 9 coulombs, okay? And then we need to actually determine both magnitude and direction. So a question sometimes may say, you calculate the magnitude of electric field at a point. In that case, direction is not necessarily needed. But when it says calculate electric field at a point, you need to get both the magnitude and the direction. Why? Because this is a vector quantity. We have said that many times before. Right, so before we look at the actual calculation, there are different units. Now, we are saying that in reality, a millimeter is actually 1 times 10 exponent negative 3 meters. So the SI unit is the meter, right? And then we know that a centimeter is equals to 1 times 10 exponent, negative 2 meters. So what do we mean when we say a millimeter is 1 times 10 exponent negative 3? You are saying that a millimeter is 1,000th of a meter, while a centimeter is 100th of a meter. So that's the mathematics around it. And then we also know in terms of charge that 1 nanocoulomb is actually equals to 1 times 10 exponent negative 9 coulombs, right? So these are some of the conversions that you need to be very comfortable around. And then the formula says E is equals to K, Q over R squared. Now, this formula is actually provided in the formula sheet. So the data sheet is something that you need to familiarize yourself with. Be able to copy the formula as it is given, do the necessary substitutions, of course, after doing the necessary conversion, if there's a need for that, okay? So the given formula, just to identify the relevant formula from the data sheet, you'll be credited a mark for that. So this is something that we need to get used to. This is the language that we talk. So copying the formula it is given is very, very important. That is worth 1 mark. So if we were to look at your work and say, okay, did the learner manage to identify the correct formula? Then if it's yes, you'd get a mark for that. I think it's simple as that. Okay, so that's the formula, and the value of the constant is also given in the table of the physical constant. So E is equals to K, which is 9 times 10 exponent 9. Okay, the magnitude of charge is negative 15, right? Times 10 exponent negative 9. Okay, divided by the distance of that point from the surface of the charge that creates the field, which is 6 multiplied by 10 exponent negative 3. But we need to square the distance. So this is the entire substitution that is correct that you need to carry out. And then subsequent to that, the issue of the calculator comes in then, right? So from our calculator, our scientific calculator, okay, it's another very important tool that you must be able to utilize correctly so, right? So here we have, okay, this is a fraction. We would say then 9 times 10 exponent 9, okay, that's the value of the Coulomb's constant, right? Remember this formula, we derived it using the law, Coulomb's law of electrostatics. So we still use the very same value of K as in the Coulomb's constant. We multiply that by the magnitude of the charge, which is minus 15, okay? Okay, that's minus 15 times 10 exponent negative 9, okay? Even if you don't put the negative, because that negative is actually going to be an indication of the direction of the field, whether it's the field is towards the charge that creates the field or it's away, right? As we shall establish, right? And then the distance is converted to 6 times 10 exponent negative 3. But remember, we have to square the distance, right? Once we've done that, you actually get the magnitude of the force that a unit positive charge will experience. We shall try and break this down. So this is like what? 1, 2, 3, 4, 5, 6. Okay, so it's like 3,750,000. Okay, so I'm gonna write that down. So E is equals to 3,750,000 Newton per Coulomb, right? So there's this negative. Now let's look at a case using the simulation in terms of trying to unpack the minors. So the charge that we have, the negative 15 nanocoulombs is actually a negative charge. So if the charge is negative, it says to us that, let's say that point is somewhere there, 6 millimeters away from that negative 15 nanocoulombs. Actually, what this says to us is that the unit positive charge at that point X actually experiences a force towards that negative charge. So that negative is actually for the direction. So if we can quickly go back to our calculation. So our E is actually equals to 3,75 times 10 exponent 1, 2, 3, 4, 5, 6, exponent 6, right? Newtons per coulomb, ne? Towards Q1, ne? So the direction is actually towards Q1, okay? So Q1 is the charge that created the field. So that negative suggests the direction of the field. So this is basically how you carry out calculations in as far as the electric field at a point, right? Now, having said that, there can be a different case. What if we had, let's say, a charge of, say, for argument's sake, plus 10, microcoulombs, right? Which is a point charge in space. So around that positive point charge, there's an electric field, as you would expect, right? So there's an electric field around that positive point charge, okay? Now we're just varying the type of charge just to emphasize the issue of direction. So the direction is away, okay? This is what we've managed to discover from the simulation. Let's say now we've got point Y, right? Point Y is, say, for argument's sake, 2 centimeters away from the surface of the charge. If we were to determine the magnitude of electric field at this point due to the 10 microcoulombs, then we would obviously have E is equals to K, Q, right, over R squared. Let's call this Q2, right, just to vary it, K over R squared, right? So E becomes 9 times 10 exponent 9 multiplied by, you do the necessary conversion, 10 multiplied by 10 exponent, micro is -6, right? Divided by the distance, which is 2 times 10 exponent -2, then we square that. Then whatever we get here is going to be positive. That positive suggests that the force is away from the charge that creates the field, right? Okay, so if the point charge was positive like that, and then we locate that, you can see that the force experienced by the unit positive charge in this case is actually away, whatever the magnitude is. Obviously, the remainder of that is the mathematics which anyone can actually do. Now, having said that, I think we try and get a sense of exactly what we talk about when we say we want to determine, electric field at a point as a vector quantity that it is, right? Now, in closing, we need also to look at, some of the key things that we try to emphasize here. And it says here, an electric field is a region in space. So this is the definition of an electric field. An electric field is a region in space in which an electric charge will experience an electrostatic force. And this electrostatic force is actually a non-contact force, right? Because these are field forces, right? And then the electrostatic force between any 2 point charges, be it the unit positive charge and the negative charge, or unit positive charge and another positive charge, is either attractive or repulsive, plain and simple, because we know from, way back that like charges will repel each other while opposite, they would actually attract, right? And then any electrostatic force is a non-contact, we've emphasized that, or a field force, okay? And is described by the Coulomb's law, which talks about the mathematical relationship between the force and the product of the charges, Q1, Q2, as well as the square of the distance. So this is the mathematical representation of the relationship between electrostatic force, product of charges, and the square of the distance. So electric field strength or electric field at a point, which is the quantity E, is a vector, okay, which is in Newton per coulomb. So this is actually the force experienced per unit positive charge. Now, in the previous example, it says that the unit positive charge experiences a force of 3,750,000 newtons is a force that is experienced by 1 coulomb of charge. That's the E, okay? And then this is actually towards Q1, right? towards Q1. So this is actually the magnitude as we would break it down, and this is actually the direction, right? And then having said that, it's obviously, we're saying that the magnitude of the charge that causes the field and the distance, this has to do with the big questions that we asked ourselves. Now, what affects the magnitude of electric field at a point? There are two things. It's how big the charge that creates the field and the distance of the point from that charge that creates the field. So that's what we wanted to discover at the end of the day, right? Having said that, and because of time constraints, we've reached the end of an exciting session. Hopefully you take a lot from our discussion that we had today. From myself, Themba Ncube, is cheers and bye-bye for now.